Let's now expand our conceptual toolbox for stoichiometry. So far, we've seen two-dimensional tools that we can use to convert from measurable quantities, laboratory quantities, into moles. Molar mass, which is grams per mole, and molarity, which is the moles of solute in a solution divided by the liters or the volume of the solution. In studying chemical reactions, we're often interested in the amount of one substance needed to consume or produce a specified or given amount of another substance, and the substances A and B may be reactants or products, which is why we use this language, consume or produced. The key to making these kinds of conversions between amount of one substance and amount of another is a balanced chemical equation and the stoichiometric coefficients that we find within. So the skill of balancing chemical equations, if you haven't picked it up already or it's been a while, it's important to dust off your balancing powers and make sure you're comfortable balancing chemical equations. We'll often see them written out in words, for example, and it'll be up to you to write a balanced equation with proper coefficients. There are two methods for balancing chemical equations, and they each have their advantages and disadvantages. The first involves inspection and kind of tinkering with the coefficients until you arrive at a balanced situation. And the second is to do an algebraic balancing that brings in a set of equations and solving a linear set of equations and all that good stuff. The inspection method is quick, but the algebraic method, if it's done systematically, is foolproof. So usually I start with inspection and then move to algebraic balancing if necessary. So let's practice this example. In this reaction, iron 3 chloride reacts with ammonium sulfide to form iron 3 sulfide and ammonium chloride. And where I like to start when balancing chemical equations is to look for elements that appear only in one reactant and one product on both sides of the equation. So iron jumps out as a good candidate here. Iron appears on the left-hand side only in FeCl3, and on the right-hand side only in Fe2S3. And so what we can immediately write here is that the ratio of those two coefficients certainly must be 1 to 2, right? And so I can write a 2 in front of FeCl3 and leave Fe2S3 as a 1 for now. If we focus now on the ammonium group, we find 2 ammoniums within ammonium sulfide and only 1 in ammonium chloride. So we need a coefficient of 2 over here at NH4Cl to make sure that we're balanced on ammonium. And this is totally fine, by the way, to balance on a fragment that does not change over the course of a reaction. Are we done at this point? Well, something that we should pay attention to is the balance of sulfide. Notice that we have 3 sulfides on the product side, but only 1 on the reactant side. So we certainly need to multiply the coefficient of NH42S by 3 to ensure that we're balanced on sulfide here. So let's go ahead and pop a 3 in front of that and see where that gets us. Well, we've made the sulfur okay, but now we've got 6 ammoniums implied on the reactant side and only 2 on the product side. So now we need to increase the coefficient of NH4Cl from 2 to 6, multiply it by 3, right? So that we have 6 ammoniums on the left and 6 ammoniums on the right. And now notice that this is pretty cool. We've just balanced for chlorine, 6 Cl's on the right and 2 times 3 equals 6 chlorines on the left as well. So now are we completely balanced? Well, we've got 2 irons on the left and 2 on the right. We've got 3 sulfurs on the left and 3 on the right, 6 chlorines on the left and 6 on the right, and 6 ammoniums on the left and 6 on the right. And so indeed, we are completely balanced. I won't show the algebraic method here. We may practice this in class, but the idea is to treat each of these stoichiometric coefficients as a variable and then write balance equations, mass balance equations, for each of the elements. So we would have one equation for iron, one for chlorine, one for nitrogen, one for hydrogen, and one for sulfur, for example. It's important to be able to balance equations, but actually it's even more important to understand what a balanced equation tells you. The power of balanced equations really is in these stoichiometric coefficients, because now we know the ratios of elements that combine in the course of a chemical reaction. More formally, a balanced equation tells us how many particles of a substance A react with or produce a substance B. The ratio of two reacting substances in a balanced chemical equation is what we'll call a mole-mole or a molar ratio. And we use these molar ratios to convert moles of one reacting substance into moles of another. So for example, in the last problem we saw that the coefficient on FeCl3 was 2, and the coefficient on Fe2S3 was only 1. And so the molar ratio between FeCl3 and Fe2S3 is 2 to 1. And we know that 2 molecules of FeCl3 react for every 1 molecule of Fe2S3 produced. This is an example of a molar ratio. And the way you would typically write this within a problem, for example, as a factor in the course of dimensional analysis, is we would write 2 moles of FeCl3 divided by 1 mole of Fe2S3. And of course, the reciprocal of this, the inverse molar ratio, is equally valid if we wanted to arrive at moles of Fe2S3. As we've just seen, we can read these molar ratios directly from a balanced equation. Figure out what substances you're interested in based on the parameters of the problem and pull their coefficients out into a ratio. It's as simple as that. On the top of the ratio, put the substance whose moles you ultimately want to find. And at the bottom of the ratio, you'll put the moles of substance that you want to cancel out. So you may know the moles of, for example, a target product that you want to produce, and you want to know the moles of a reactant that you need to produce that amount of product. You would put the reactant on the top of that ratio and the product on the bottom. Let's do a quick example here. How many moles of sodium bromide are produced from the reaction of 30 moles of Br2? So this is kind of going in the opposite direction. We know we've got 30 moles of Br2, and we want to know how many moles of sodium bromide we can produce from the 30 moles of Br2. The coefficients here are 2 sodium atoms, they're drawn for you here and here, plus 1 bromine atom, plus 1 bromine molecule. Br2 produces 2 molecules of sodium bromide. So to set this up, we start with what we know, the 30 moles of Br2, and now from the balanced chemical equation, which is given to us in this case, we can simply use the molar ratio. We can simply pull out the molar ratio that we need. In the denominator, we put the moles of substance we want to cancel, 1 mole of Br2, and I put 1 mole there because the coefficient here is 1, to 2 moles of sodium bromide, and this is a very simple calculation, and we get 60 moles of sodium bromide produced in the course of this reaction. So a very straightforward calculation, but these molar ratios are very powerful for reaction planning because we can go from an amount of any substance given to us to an amount of any other substance using stoichiometric coefficients and molar ratios. Most practical problems are going to involve arriving at a final mass of reactant or product or a solution volume, because these are the quantities we use in the laboratory, right? Masses and volumes are the norm. But molecules don't really care about mass and volume, right? Molecular behavior is not simply related to mass or volume because molecules have different masses and different volumes. It's simplest to understand and work with reactions when we use number of moles and amount of substance. And so my advice to you when you're doing stoichiometry problems is to convert to what I call mole land as early as you can when solving problems. If you're in mass or laboratory land, if a problem gives you masses or solution volumes, use molar mass or molarity to convert from mass land to mole land as quickly as you can. Because once you start working with moles, you can start using balanced chemical equations and molar ratios, and it makes things conceptually a lot easier than working with masses. It's just less taxing on your working memory. So let's do a quick example of a little bit of reaction planning. Copper 2 plus reacts with aluminum metal according to the balanced equation shown here. What mass of aluminum is needed to completely consume 0.3 grams of copper chloride dissolved in water? So copper 2 chloride, by the way, dissociates into 1 copper 2 plus ion and 2 chloride anions. This is important to the problem only to the extent that it allows us to recognize that for every mole of copper chloride dissolved, we have 1 mole of copper 2 plus. That's a molar ratio. And so we can basically treat whatever number of moles of copper chloride we've got here as the number of moles of copper 2 plus. that we end up with. But it is important to notice that we're working with a mass of copper chloride here dissolved in water. We need a number of moles of copper 2 plus, and the way to get there is to take the mass of CuCl2 that we're given and divide that by the molecular weight of CuCl2. The given mass is 0.3 grams, and the molecular weight of copper 2 chloride is 134.45 grams per mole. This gets us to a target or a given number of moles of copper chloride of 2.23 times 10 to the negative 3 moles. Ultimately, we'd like to know the mass of aluminum that is required to completely consume this amount of copper 2 chloride. And briefly remember that the moles of copper 2 plus is simply equal to the moles of copper 2 chloride, so I'm going to stop referring to copper 2 chloride and just refer to the copper 2 ions that are dissolved in solution. To get to that mass, we can't get there directly. We need to use the molar ratio of aluminum to copper in the balanced chemical equation to find the moles of aluminum and then convert to mass using the molar mass or molecular weight. So the molar ratio here is 2 to 3. So if we take this and multiply by 2 moles of aluminum for every 3 moles of copper 2 plus, we arrive at the moles of aluminum that we would need to completely consume this amount of copper 2 plus. And that comes out to 1.48 times 10 to the negative 3 moles of aluminum metal. And notice this is just 2/3 of the number of moles of copper 2 plus. To convert this to a mass, we can simply multiply by the grams per mole for aluminum. The molar mass of aluminum is 26.98. And doing that multiplication, we end up with 0.0401 grams of aluminum metal needed to completely consume all of the copper 2 plus dissolved in solution when we dissolve 0.3 grams of CuCl2 in water. To review the process one more time, we did have to notice that CuCl2 dissolves in water to give 1 copper ion, so there's a mole-mole ratio thing going on there. We convert the mass of copper chloride into a moles of copper 2 chloride, use the 1-to-1 ratio to just proclaim that that's equal to the moles of copper 2 plus in solution, use the molar ratio of aluminum to copper 2 plus to get moles of aluminum, and then converted that to a mass using molar mass. So what we're doing here is a kind of dimensional analysis where we're bringing in all of the conceptual tools of stoichiometry: mole-mole ratios, molar mass, and where we would need it, molarity.